This lesson's on oscillations and simple harmonic motion, and here are your objectives. Now first, an oscillation is simply a back and forth motion. A common example is a mass on a spring. Imagine we had a mass here on a frictionless surface with a spring attached to it. We could pull the mass out to here, and that would stretch out the spring. And then we could let it go, and it would spring back, and it would pass through the initial resting position, and it would end up compressing the spring, and then the compressed spring would try and spring back towards the resting position, and this mass would oscillate. It would vibrate back and forth around this position, and we call this resting position of the system the equilibrium position. And the force that the spring is exerting here is trying to pull it back to that resting position, and so we call that spring force, in this case, the restoring force. So we get an oscillation when we have a system that is brought away from its resting or equilibrium position and a restoring force that's trying to get it back to that position. Now in this case, we would have repeated cycles of the mass oscillating backwards and forwards. And a cycle is just one turn from a position all the way back to the same position moving in the same direction. So if we started out at the red extended position here, we let it come all the way back to the left and all the way back to the right. That would be one cycle. Now if this equilibrium position was at 0 meters, let's say that the stretched out position was at positive 4 meters, we'll make right positive, and the compressed position was at negative 4 meters. This distance here between the equilibrium position and one extreme, that distance we would call the amplitude, which we give the symbol A. And here the motion is symmetrical, so we have another amplitude here. In other words, to go through one cycle, you're actually going through, one cycle is going through 4 times the amplitude, because you go through an amplitude here, a second, then a third, and then a fourth. Now we could graph this if we put displacement, or rather position, on the y-axis. We could graph this, and let's say that we started out at the 4 meters to the right position, the red stretched out position, and we got back to the equilibrium position at 1 second, to the left at 2, then at 3, then at 4. These are difficult to draw smoothly, but it might look something like that. And if we did it again, go through a second cycle, then it might look something like that. Again, it should look more smooth, and I'm trying to draw something sinusoidal here, although I haven't really managed to. Now my time axis wasn't labeled, but this is time in seconds, and so we can define the period, which we give the symbol capital T, T for time, as the time to complete one cycle, and that's going to have units of seconds, because that's our SI units of time. And so we can find the period by looking from a crest to a crest of the graph. So here's a crest, here's another crest. This has got time on the x-axis, so that means that this is the period. Similarly, we could look from this position to this position on the graph, and that would be the period. And in this case, we can see that the period is 4 seconds. The frequency is the inverse, or the reciprocal, of the period. It's the cycles per unit time, and if we're using seconds for period, then frequency is going to be in seconds to the -1, which we also give the special symbol of hertz. And that's because we're dealing with cycles per second, but cycles is not really a unit, so that disappears and we end up with seconds to the -1. So here we can see how to find the period from the graph, and the amplitude is just here, right? It's the distance from the equilibrium position to the maximum displacement, or similarly, that would be the amplitude there. And I mentioned the relationship with period and frequency, but I didn't write it down. I said that they're reciprocals of each other. So the formula is here, that the period is equal to 1 over the frequency, or similarly, the frequency is equal to 1 over the period. So I said above that I was trying to draw a sinusoidal graph, or a graph in the shape of a sine curve. And oscillations that have that kind of sinusoidal shape are called simple harmonic motion. That harmonic word means that it's sinusoidal, taking the shape of a sine or cosine curve. And this is a special case of oscillation. And to get simple harmonic motion, to get this kind of sinusoidal displacement time graph, you need 2 special circumstances. both having to do with the restoring force. You need the restoring force to be proportional to the magnitude of displacement from equilibrium. What do I mean by that? Well, that means if we move the mass 2 times as far from the equilibrium point, we should have a restoring force that's twice as great. The second characteristic of simple harmonic motion is that the restoring force is directed towards the equilibrium position. So if we displace to the right, then the restoring force pulls it back to the left, back towards the equilibrium position. We can summarize both of these in one statement of proportionality. We want F, this is the restoring force here, to be proportional to the negative of the displacement. This negative here is the second part of our definition. It's the fact that it is being pulled back towards the equilibrium position. And this is, of course, the fact that it's proportional to the displacement. So if we double x, we double the force. And if x is positive, meaning to the right, if the displacement is to the right, then the force is to the left. So this statement captures both of these characteristics. Now we can turn this into an equation by introducing a constant. And if we call that constant k, you'll recognize this as being very familiar from Hooke's law. This is the restoring force that's acting in a spring when a mass on a spring system is displaced from equilibrium. And so in fact, this system that we've been using as an example is actually an example of simple harmonic motion because it obeys these two characteristics that we need for simple harmonic motion. So let's look at this system a little bit further than this mass on a spring. If you were to observe this mass on a spring oscillating backwards and forwards after you pulled it out to an extreme, so I'll pull it out here, and I'm not going to draw the spring this time just so that I don't make the diagram too messy, you would see it oscillating backwards and forwards from the red and the blue extremes and passing through the middle. Now, at the edges here, it's turning around, and so as it's turning around, it must have a velocity of 0 instantaneously because it's going from a positive or a rightwards velocity, we'll call right the positive direction, to a leftwards and vice versa. Now, remembering that the force is proportional to the negative of the displacement, if the displacement is 0 in the middle, here the displacement is 0, then the force is going to be equal to 0 as well, and therefore the acceleration is going to be equal to 0. So the acceleration is 0 at the equilibrium position, and so is the displacement, and the velocity is 0 at the extremes. So what you're seeing happen is a mass oscillate backwards and forwards with maximal force, maximal acceleration being exerted by the spring at the edges, and then it coming back towards equilibrium and shooting right through, even though there's no acceleration at the equilibrium position, it's already got a high velocity, and in fact, it's got a maximal velocity at the middle. So if we look at the three quantities, position, velocity, and acceleration, the velocity is maximal at the equilibrium position, while the magnitude of the acceleration, and I'm just going to deal with magnitudes here, is maximal at the extremes. And of course, the position is maximal at the extremes as well. The acceleration is 0 in the center because the spring is neither compressed nor extended. It's at its resting position, so the force is equal to 0. And of course, the displacement is as well. Now, at the edges, we said the velocity must be 0 because it's turning around. And if we just define right as positive and left as negative, then the displacement is positive everywhere over here. If this is the equilibrium position, I'll mark the middle there. Right over here, displacement is positive, and over here, displacement is negative, and right in the middle we said displacement is 0, so here displacement is negative. Once you're to the right of the equilibrium, as you're moving from here to here, acceleration is going to be pulling you, or the force is going to be pulling you back in that direction, and so acceleration is going to be leftwards. So if you are displaced to the right of the equilibrium, acceleration is left, and if you're displaced to the left of the equilibrium, then acceleration is pointed to the right, as the force is. Again, remember that the acceleration is proportional to the negative of the displacement, so the signs of these two are always going to be opposite. Now, velocity is a little bit more involved because with these rightward positions, you can be moving to the right? You could be going from here to here. You could be stopped at the end where you are momentarily not moving while you change direction, or you could be moving to the left. And so in both of these cases, the velocity in this leftward region and in the rightward region can be positive, negative, or 0. So there's a summary and an explanation of the signs and the relative magnitudes of position, velocity, and acceleration. One more thing just to introduce, which I'm not going to derive a proof for, but I'll just tell you, and then you can solve some problems with it, is the period of a mass on a spring is equal to 2 pi times the square root of the mass of the object divided by the spring constant k. So that means that if the mass gets bigger, then the period will get bigger because there's more mass to move, greater inertia, so it takes longer to do that. And if the spring gets stiffer, higher k value, then there's more force exerted per unit stretch, and so you get a shorter period. It's going to move backwards and forwards faster. Now, a key thing to note here is that amplitude does not affect period, and that can seem very strange. But what that means is, no matter how far I pull this outwards or squish this backwards, its period is going to be the same as it oscillates backwards and forwards. Its period is determined once we have a given mass and a given spring. It's not affected by the amplitude that we stretch it out to. So that's a summary of oscillations and simple harmonic motion.